Hello, Algebra 2 CP students. Hopefully, you're having a great day so far. I'm recording this video in the midst of a nor'easter, so hopefully, you're staying safe and warm. It is pretty crazy out there. Today, what I would like to do is I would like to talk about more applications of quadratic functions, namely applications related to area and geometry. Before we do, I think it's beneficial just so one is on video and also to review concepts with you on projectile motion. I think it's beneficial to talk about one projectile motion problem and have you guys try one on your own first to see if you can figure that out based on what we talked about on Monday. So if you could, take just about 5 minutes, pause the video, see if you can figure out how to do this projectile motion problem on your own. We'll go through it together and go from there. All right, hopefully by now you've paused the video, you've tried this problem on your own. It states that Legolas, the greatest archer in all of Middle-earth, of course, fires an arrow upwards from the top of a 116-foot castle. If his arrow has an initial velocity of 224 feet per second, after how many seconds will his arrow reach its maximum height, and what is the maximum height? So just like we saw on Monday, what we need to do with this function is use our projectile motion formula, fill in our initial velocity and initial height, and then find the vertex of that function, because the vertex will represent the maximum. That's what a vertex is. On a parabola, it's either the maximum or the minimum. The x-coordinate of the vertex represents how much time it will take for the projectile to reach its maximum height, and the y-coordinate represents what that height actually is. So let's figure that out. First, building our function, we'd say it's h of t is equal to, we'll carry down our negative 16t squared. Our initial velocity is given to us. It says it's 224 feet per second. And our initial height is also given to us. He's on top of a 116-foot castle, so plus 116. We can now go ahead and use our negative b over 2a concept to find the x-coordinate of the vertex. I would say that t equals negative b over 2a, because remember, this is in standard form. Standard form looks like this. A x squared plus bx plus c. And the vertex of anything in standard form, the x-coordinate is negative b over 2a. And the y-coordinate, we would take that value and plug it in. It's f of negative b over 2a. So to get t, we do negative b over 2a. That's going to be negative 224 over 2 times negative 16, which is negative 224 over negative 32, which I believe is positive 7, but I'm just going to double check on the calculator. Negative 224 divided by negative 32, yep, we get 7. So what that answer of 7 means is that means it takes 7 seconds for this arrow to reach its maximum height. It's a fantasy world, you know? Think about that. 7 seconds in the air, it's just climbing upwards. It's pretty awesome. I mean, it's Legolas after all. What do I do with that 7 seconds to figure out what the maximum height actually is? Well, I'm going to take that 7, plug it into my function here, and we can say that the height after 7 seconds is negative 16 times 7 squared plus 224 times 7, oh, not times t, times 7 plus 116. And with a little bit of calculator magic, we can figure that out here. 7 squared is 49 times negative 16. We'll get negative 784 for that first term there, plus 224 times 7, that's 1568, which I believe will give us now positive 784, and then plus 116, I believe that comes out to be 900 feet. So the solution to this problem would be that it takes 7 seconds for the arrow to reach its maximum height, and that maximum height is 900 feet. So if you notice, all we really had to do was just find the vertex. It's the same thing that we'd have to do if I asked you to sketch a graph of that function. I certainly wouldn't, because you'd have to go all the way up to 900 on the y-axis, but the same principle would apply. You'd find the vertex by doing negative b over 2a, taking that value, plugging it in to get the y-coordinate. And we know that that's the maximum because it's the vertex. It's not just a random value. It's the vertex. It's always the maximum or minimum. All right, hopefully that made sense. Let's transition now into, if you have any questions on projectile motion, I'm happy to answer them. But let's transition into our geometry style word problems. You ready? Here we go. Looks like this. So consider a problem like this. It has to do with area because we've already explored area when we did solving quadratic equations. We took a look at some applications of area. Of course, when we're talking about finding the maximum and minimum, we can look at applications of area as well. This one states, you have a 1,200-foot roll of fencing and want to fence in a rectangular area and further divide it in half as shown in the diagram. So you see here we have the length, the width, and we're further dividing it in half. What are the dimensions of the largest possible enclosure? Well, you could picture that this would be a useful type of problem in the real world because, say, you're constructing a garden or a pen or something like that that you need to fence in, maybe something for your dog or for your pet. You want to fence in this area. You want to make sure you make the most of what you purchase. If you purchase this roll of fencing, you don't want to be inefficient. You want to try to maximize the amount of space that you can enclose. Well, in order to figure that out, we of course know that the area of any rectangle is its length times its width. But if I just start with area equals length times width, I currently have way too many variables. I don't know any of these things, so I don't really have anywhere to get started. But I do know that my roll of fencing is 1,200 feet. And that 1,200 feet is going to represent the distance of this and plus this, plus this, plus this, and plus the middle here, right? Think of that. If I'm rolling out all 1,200 feet of this fencing, and of course I want to use all of it to maximize it, then I need to use it everywhere. The distance of the entire outside plus this middle section should represent that 1,200 feet. It's kind of like the perimeter. It's not exactly because it also includes this middle section here, but it's that same concept. So we'd be able to say that with my 1,200 feet, right, I need to build this measurement and this measurement. How many times do I need to build this measurement of the length going this way? Well, I need to build it twice. I need to build it once here, and I need to build it once here. So I know that in my 1,200, I'd have to construct the length 2 times, or 2L. And also, I'd have to construct this measurement from here to here 3 times. I'd have to construct 2 L's and 1, 2, 3 W's. So I would say that 1,200 would equal 2L plus 3W. Because 2 times this measurement plus 3 times this measurement, I want that to equal my 1,200. Hopefully that makes sense as to how we create that equation. Now what we can do with this equation is I can use this to get one of the variables by itself. Once one of the variables is by itself, we substitute it into here. That will allow us to create a quadratic equation, and then we can do our good old negative b over 2a to find the maximum. All right, take a look at what that's going to look like. It doesn't matter which one of these two variables you try to get by itself. You could try to get L by itself, or you could try to get W by itself. Just for the sake of picking one, let's try to get L by itself. So if I wanted to get L by itself, we could subtract 3W from both sides. We would get 1,200 minus 3W is equal to 2L. Now I can divide everything by 2, and we'd be able to get the expression that 600 minus 3 halves times W, or 1.5 W if you want to put it that way, but I'll leave it as a fraction, is equal to L. Now that we know that 600 minus 3 halves W is equal to L, I can use this information and plug it in to my area formula right here. Because I can now say that the area of this rectangle is length times width, but we now have a new name for the length. We can call the length 600 minus 3 halves W times W. See how what we did is we just substituted our new expression for the length. All right? You may think to yourself, well, what's the benefit of that? The benefit of that is now if I distribute the W and move some terms around, take a look at what we're left with. I can say that the area equals, if I distribute the W to both, and I switch the terms around so that W squared is going to be first, I'll get negative 3 halves times W squared plus 600w. And if you notice, that is now a quadratic equation in standard form. Yes, my plus c here, my constant, is 0, but that's okay. We still have our ax squared plus bx plus c, which is 0. And because I have a quadratic equation, I can now find the maximum by doing negative b over 2a. All right, so hopefully that makes sense so far. Let's do it. I can now say, well, my maximum width, right, would equal negative b over 2a, because I can find the vertex to figure out, well, what's the maximum should be. What's the maximum measurement? That's going to be here, negative 600, that's b, over 2a, 2 times negative 3 halves, right? Which I know looks scary, but it's not, because the 2's are going to cancel out. We'll get that that's negative 600 divided by negative 3, which is 200. And so that tells me that this measurement here, here, and here should be 200 feet. How do I now, so that's like half of my puzzle solved. I figured out I'm trying to find the dimensions. So I got the width. That means the width that's necessary to maximize this would be 200 feet. How do I now get the length? Well, you have a couple options to get the length. But personally, I would take this 200 and plug it into here, because we have an expression that now tells us what the length is. We came up with this at the very beginning of my problem. I said, well, if I know that my width that maximizes all of this is 200, let's take that width and put it all the way back into here, and that will tell us what the length is. Because now we can say that 600 minus 3 halves times w, but we now know w is 200, should equal the length. That maximizes the area. Hopefully that makes sense. Notice we wouldn't just plug it back into this original equation up here, our quadratic equation, because this would tell us what the area is. And certainly you could then like work backwards and say, oh, the area divided by the width would be the length, but I think that makes it more steps than it needs to be. Now, certainly if the problem asked what's the area, then you could take that 200 and plug it in here. But you could also take that 200, plug it in here to find the length, and then do length times width to get the area. So there's a couple different options that you have. Anyway, to find the length, we would now say that 600 minus 3 halves times w is going to be minus 300 is equal to L. And so we would get that the length is 300. And so the dimensions of this enclosure that would result in the largest possible area would be 300 for your length by 200 for your width. Okay, and that's feet for both. All right, and that's keeping in mind that you have to construct that middle barrier as well. You might be like, well, hold on, 300 times 200, that's not 1200, right? But the idea is that you also have to construct this middle barrier. Any question about that at all? Hopefully it's sinking in. Hopefully it's making sense. Again, if you do have a question, though, please feel free to reach out to me. My email is right on the screen, so you can contact me. All right. I have one more to show you on the same sort of area concept, and then we'll go from there. Again, keep in mind that if it asked you to physically find the area, you could then take that and plug it in. All right. You may also notice that I mentioned that 300 times 200 is not 1200. It certainly shouldn't be, because this doesn't represent the area. But you may also notice that it's not the perimeter either. 300 plus 300 plus 200 plus 200 isn't 1200, because you also have to account for this middle barricade. That is what bumps it up to 1200. All right, anyway, moving on. Next question. Let's do it. Let's do it. But you didn't know these were all prepared ahead of time. Full of surprises here in an Algebra 2 video. It says, a shepherd wants to make a rectangular pen for his sheep next to his barn. He has 60 meters of fencing to cover 3 sides of the pen, with the 4th side being the wall of the adjacent barn. What are the dimensions of the largest possible enclosure? So what's happening here is, instead of constructing an additional side, which is what you saw in the previous problem, we're now constructing one fewer side. So think of the fact that we have a barn here. This will be my great drawing of a barn. There it is, barn. And on the side of that barn, we're constructing this sort of pen here, where I have this is my length and this is my width. And notice that one of these sides is adjacent to the barn. It says it right here. He has 60 meters of fencing to cover 3 sides of the pen, with the fourth side being the wall of the adjacent barn. So we don't have to expend resources in order to build this fourth side. We're just building it against the wall. So picture that we have to construct 1, 2, 3 sides. Okay, hopefully that makes sense. And then, of course, we're trying to find what the largest possible enclosure is. So, of course, we know that the area, just like before, is length times width. But in order to get any progress to be made on that front, we first have to manipulate our equation a little bit using this 60. We know that the 60 meters of fencing that is required to cover this needs to build this length, this width, and this length. I need to use my 60 meter roll to build this, this, and this. So that means I have to build 2 L's and I have to build 1 W. 2 segments of length L and 1 segment of length W. We can now try to get one of those variables by itself and plug it into the function. The last example, we got L by itself. This time, let's get W by itself. So let's subtract 2L. It doesn't matter which one you pick. You'll just solve for them in a different order. I would get 60 minus 2L is equal to W. Right? Now that we know that W can be written and expressed as 60 minus 2L, well, let's use that information to plug it into the formula, right? And that will tell us that our area should equal the length times the width, but we're not going to call it the width anymore. It's now going to be 60 minus 2L. If we distribute that length and then rewrite our terms to get it in our quadratic standard form order, we would say here that the area is L times 60, L times negative 2L, right, a little distributing. We'd get negative 2L squared plus 60L. And again, plus 0 for our C. But we now have our quadratic in standard form, ax squared plus bx. Now that we have that, we can find the maximum length by saying let's do negative b over 2a, because that will find the vertex of whatever that is. And we know the vertex represents the maximum. That's going to be negative 60 over 2 times negative 2, which is negative 60 divided by negative 4, which comes out to be 15. So if my length that maximizes this enclosure has to be 15, well, we can find the width by saying, let's take this 15, let's plug it back into here, and figure it out. That means that 60 minus 2L, or 2 times 15, would have to equal the width that makes this enclosure at its maximum. Well, that means 60 minus 30 would have to equal the width, and the width would equal 30. And so the dimensions that would maximize this enclosure, considering that you do not have to build the fourth wall, would be 15 for your length by 30 for your width. And this is in meters. All right. Once again, I want to emphasize that if this problem asked you, it doesn't, but if it asked you to find the area, you could then physically multiply those things together and just get that your area is, what is it? I could probably figure that out. 30 times 15 would be 450 square meters. Okay, it doesn't ask you for that in this problem, but if it did, you certainly could figure that out. All right. Hopefully that made sense. Let me just recap the process quickly. So we did a projectile motion problem at the start. I think that was pretty a-okay. What we need to do is we essentially have two equations, two relationships going side by side here. We have the area and we have this concept related to the perimeter, or like how much we actually have to build. Here you notice that in order to construct this structure, I need to build this measurement of L 2 times and this measurement of W 3 times. And I have 1,200 feet worth of fencing or worth of materials in order to make that happen. Doing a little bit of algebra, we can get one of those variables by itself. And once we do, then substitute into the area function. That allows us to get a quadratic function that we can then use our vertex concepts with to find the maximum. The negative b over 2a gets us the maximum value for the width. We could take that value then and plug it back into our other function to get the value for the length. If it asked for the area, we could of course do length times width, or you could take this 200 and actually plug it into here, because if you notice, that gives us area. Same process happened over here. We noticed that instead of constructing an additional side, this one we had to construct one less side, right? We didn't have to do this, so we only had to worry about 2 L's and 1 W when we were building this. But the same process applied. We used our 60 to come up with an expression for W. Took that expression, substituted in here. It resulted in a quadratic. We used negative b over 2a to find the maximum. Took it and plug it back in to find the other measurement. We will have more time to practice this later in the week and into next week, but hopefully nobody has any questions, comments, or concerns on this front. If you do not hesitate to reach out and ask. I encourage you to try more practice problems on Google Classroom as well. The answers are provided for you. And I hope that you have a great rest of your day and stay warm. It is windy and snowy and crazy outside. So have a good one, everyone. Take care.